This part of the sky is called Ursa Major, the constellation of the Great Bear. Here we see the Big Dipper in the upper part of Ursa Major. The brighter stars are labeled with Greek letters. This star is Xi of the Great Bear. In Latin, Xi Ursae Majoris. Xi is 26 light years away. Let's have a closer look. We are now 6 light days away. Xi appears as a pair of stars moving around an imaginary point called the barycenter. The barycenter is not exactly midway between the stars. One star has more mass than the other and must be closer to the barycenter. The brighter, more massive star we call the primary. The other star we call the companion. Astronomers followed the motion of these stars with telescopes and found the point that didn't wobble as the stars revolved. In this way, they located the barycenter and calculated the relative masses of the stars. The path traced out by each star is an ellipse, exactly the kind of orbit produced by gravitational attraction. We therefore believe that these stars are bound together by the same kind of force that holds the planets in orbit around the sun. The mathematical laws of motion require that the barycenter lie at a focus of both ellipses. Notice that the stars move faster when they are close to the focus. We are looking at these orbits face on, but from the Earth we see the orbits at an angle. This is the way they appear from Earth, tilted through an angle of 57 degrees. Although the shapes of the true orbits now appear distorted, these curves are also ellipses. But notice that the barycenter no longer lies at a focus of these ellipses. This observation convinced astronomers that we were not looking face-on at the orbits. Once the orbits were measured precisely, astronomers could calculate the 57-degree tilt that would put the barycenter at the proper point on the true orbit. If you look at Xi with a small telescope, even a 2-inch telescope, you will be able to see these two stars. But with the best observing conditions and the biggest telescope, the turbulent atmosphere of the Earth blurs the image. A very good photograph would show the stars as fuzzy disks about this size. And so it is difficult to measure the relative positions precisely. The motion you see has been speeded up enormously so that 6 years of motion occur every second. Actually, the time required for the stars to make one trip around is about 60 years, and we see it in 10 seconds. Let's quickly review the history of observations of our star. The 2 separate stars in Xi were first discovered by William Herschel in 1780. Astronomers then measured the changing positions of the stars, and in 1827, before a complete revolution had been made, the tilt and orbit were computed from Newton's laws of motion by Félix Savary. In 1900, the primary, and then in 1918, the companion were observed with a spectroscope, and surprising new information was obtained. But we must take an even closer look to see what was discovered. Let's slow our time rate so 1 year passes in 2 seconds. And let's center on the primary star. Here, the period of revolution is 1.8 years, and the distance between stars roughly half the distance from the Earth to the Sun. Next, let's examine the companion star. Now we set the time rate at 2 days per second. The period is 4 days. These stars are as close together as the Earth and the Moon. We are close enough for the first time to see the actual disks of these stars. Xi is, in fact, a 4-star system, a quadruple star. The distance between the primary and companion pairs is about 10 times the Earth-Sun distance. Binary stars and multiple star systems like Xi are very common. At least 1/3 of the nearby stars are, in fact, binary or multiple systems. All our knowledge of the masses of stars comes from observations of nearby binaries.